Hello my dear students, a very good morning to all of you. So as you know, in previous class we have discussed with the concept of metals and non-metals. In that you have studied about occurrence of the metal, and I told you that you must and should remember the reactivity series. So I hope now you are able to write the reactivity series. So occurrence of the metal, in that concept we have studied what do you mean by the ore, what do you mean by the minerals and conch. So these are the three concepts what you have learned. After that, the metals of ore. So you know that ores are the substances which has the more concentration of metals. So the metals are present in the more concentration, that is called as a ore. So in the ore, as we know, it has the metals. So the metals are classified into basis of reactivity in a series. There are three types. One is metal at high reactivity, one is at metal at medium reactivity, and other one is metal of low reactivity. So what this is discussed in previous class. So metal of high reactivity, metal of moderate, or metal of medium reactivity, or the metal of low reactivity. And here remember one element will come, that is the mercury, Hg. Okay, so these silver and gold are the found in native state. That means it is the pure, it can be extracted in the pure. So there is no need of any extraction method. So these are in the pure form. And even Hg is considered as a low reactivity series. The mercury is considered in the low reactivity series, but this copper and mercury both also we will consider sometimes on the basis of availability. We will consider these both as a low reactivity series. So only these two we are using at the low reactivity series, and others are reactive, and these are the highly reactive. Then these two are found in a pure state, that is our native state. So this is about what you have learned. And today, how the process for the metal of high reactivity, metal of the medium reactivity, metal of the low reactivity we will study. So before going to that, that is the enrichment of the ore. So in that, extraction of the metal of low reactivity. First we will study for the low reactivity what is the method. Then we will go for the metals of medium reactivity. Then we will go for the metals of high reactivity. So here the metals of low reactivity. So that means in the reactivity series, metal of low reactivity. So we don't need the silver and the gold. Okay, so why we don't need? Because these are in the native state. Then which one you will consider? One is the mercury and another one is the copper. These are the only two elements which we can consider in the low reactivity series. Extraction of the metal of the ore which is present in that metal is present in the low reactivity series. So copper and the mercury. So here we are using copper and mercury. And from the table, this metals of low reactivity is not, so as it is a low reactivity, is not present in the free status. So it is not available in the metal form. It may be present, it must and should present in the form of sulfide ore. That means the sulfide ore contains that metal. Which metal? The low reactivity metal. One is mercury and another one is the copper. That means it is the copper or the mercury present in the sulfide ore form. Then by the roasting method, so by the roasting method we will get the metal. So roasting is the process which we are using for the sulfides. So whenever there is a sulfide ore is there, the roasting process we will do, then there is a formation of pure metal will be there, then there is a refining of that metal will takes place. So this concept, this metal of low reactivity we will study. And remember that the metals of low reactivity, the metals are present in the form of sulfide ore, and whenever there is a sulfide ore, there is a roasting process. So after the roasting we will get the metals, that is a pure metal. So first we will study about the extraction of metals of low reactivity series. So this is what we are discussing. So in that, as I told, remember that there are two elements, two metals, so which are present in the low reactivity series, and these low reactivity series metals are present in the form of sulfide. So sulfide is nothing but, yes, that is the sulfur compounds. So metal sulfide, so it is the formula of Hg, yes, so that is mercury sulfide. And another one, as I told, it is the copper sulfide, Cu2, yes. And remember the name, that is the mercury sulfide and copper sulfide, and the common name for the mercury sulfide is cinnabar. So it is cinnabar. Okay, this is the common name for mercury sulfide. So you have to remember this name also. The ore present in the mercury, that is cinnabar. The mercury, so even it will come in the multiple choice question also. So you have to remember the ore name. The name of the ore where the metal present is the mercury, that is a cinnabar. So you have to remember, that's why I have given the name. So for this one it is a copper sulfate. Now this is the ore, okay, which is the ore for mercury, that is the cinnabar, and which is the ore for copper, that is the copper sulfate. So you have to remember the both, it is the mercury sulfide and the common name, the ore name is cinnabar, and this is the copper sulfate. So now, as it is the low reactivity series, it is not possible to extract at one step. So there is a, and you remember that whenever there is a sulfide is there, so that time it is not possible easily to break down the reaction or the bond between these two elements. So that's why first we are converting this mercury sulfide or metal sulfide to the metal oxide. So we are converting this one to the metal sulfide to the metal oxide. That means the first method is the metal sulfide we are converting to the metal oxide. So how to convert then? So how to convert this one, metal sulfide to metal oxide we have to convert, and after that this metal oxide we have to convert to the metal plus of something. So how to do this one? So one example we will take, like which one that is cinnabar, that is a mercuric sulfide we will take, Hg, yes. So I have to convert this one a metal oxide. So for that what you will do, in presence of oxygen you will roast, in presence of oxygen you will roast, as the process as you have observed, that is the roasting. So in presence of oxygen, here only I wrote, or you can write roasting or heating this one. So if you heat any mercuric sulfide or any metal sulfide in presence of oxygen, then that process is called as roasting. The metal sulfide, if you heat in presence of oxygen, the ore which is heated in presence of oxygen, that process is called as roasting process. So what happens when the roasting process takes place? The oxygen will get attached to this one and there is a formation of metal oxide. So which is the metal here? That is the mercury, that is Hg, and oxygen will combine with this and it will give the metal oxide plus of S is there and even oxygen is there, so it will give SO2. And now you have to balance the equation. Hg is 1, Hgn is 1, SO2, SO here it is 1 is there, so there are 3, so it is not balanced. So for that you have to balance now. So if you consider as it is 3, so I will write here. Now it became, so if you write here 3 2s are 6, then it will become 3 here, so Hg will be 3, so which is not possible. So what we can do, 3 2s are 6, if you write 2 2s are 4, then if you add 2 here, then it will become 2, that you can do. 2 2s are 4, so oxygen will be 4. We want 6, so we'll add that one here. So now you can observe 2 oxygen, here 4 oxygen, that means 3 2s are 6, oxygen is balanced. Then what about sulfate? Yes, that is 2 S and here 2 Hg, that means if you add 2 here, 2 Hg and 2 S, so now the equation is balanced. So this is what we got from the metal sulfide. So name of this metal sulfide, that is cinnabar, or you can even write this name as mercury sulfide. And in presence of oxygen, or you can say in presence of air, you are roasting or heating to give mercury oxide plus sulfur dioxide. So O2, that is sulfur dioxide, and this sulfur dioxide has a very bad smell. Okay, you can, whenever there is a reaction and this is present in the gaseous form, so as there is a form, fumes will be there, the sulfide shows the very bad smell nature. So from that we can guess there is a evolution of a sulfur is there. So from that we can observe this one. Then now we got metal sulfide, that is our ore of the metal, low reactivity metal, that we have converted to the metal oxide. So from the metal oxide, that is 2HgO, we want the metal. So for that no need to any other thing, just if you heat that one, this metal oxide will get converted to the Hg plus O2. Then as it is the Hg2 and O2 is 2. So this is the liquid. So mercury is present in the form of liquid, and this is the gas, and this is also gas here. Okay, so when you will heat, you will get the Hg, so which is our pure mercury metal. So from this is the process how we are extracting the metal, which is the low reactivity metal. What is the method? First, whatever the ore is there, that we will heat in presence of oxygen. So how the process of roasting will be there, like for example, if this is the cinnabar, so this is the metal. So what we will do, in presence of oxygen we will heat that one. So we will pass, there is the presence of air is there, then if you heat this one, that time it will get melt, and there is a formation of mercuric oxide, HgO. This mercuric oxide, again if it is heated, then there is a formation of mercury metal plus oxygen, so which is our required metal. So this is the one example, that is mercuric sulfide. Then another example you have to write by using copper sulfide. So here this copper sulfide reacts with, so as you know, first the metal sulfide. So this copper sulfide, you can say even copper glance also. Okay, copper glance also. So this copper sulfide in presence of oxygen, if you roast, so as it is present in the sulfide form, that is the ore of the metal, low reactive ore of the metal, so that is copper sulfide. So when copper sulfide in presence of oxygen, if you are heating, that process is called as roasting. So when there is a roasting, there is a formation of copper oxide, that is Cu2O plus of this copper oxide, or cuprous oxide we can call. Chemical it is called as a cuprous oxide plus SO2. So now you have to balance the equation. SO2, Cu is 2, but SO3, it is oxygen is 3 here, so you have to balance for that. So if you add 2, then it will become 4. So 4 and 5, so it is not possible, so we'll write 3 here. 3 to the 6, 2 to the 4, 5 and 6 will add here. So now it is balanced. 2 to the 4, 2, 5, 6, 3 to the 6. Now it is balanced. So what about copper? It is 2. And what about sulfur? So sulfur, it is 2 here, so you have to adjust that one also. So we'll add here 2. Now 2 to the 4, 2 to the 4, and 2 sulfurs. Oxygens are 2 to the 4, 5, 6. So oxygen are 6. Now everything is balanced. So now we got cuprous oxide. So that is copper oxide term. So okay, now it is copper oxide. Better you write cuprous oxide. Okay, when you this we have to convert to the metal, yes. So to convert that one, remember here, So to convert this one copper oxide, to convert this one, as you observed in the mercury, if you heat that one directly, it will get converted to the mercury metal. But in case of copper, to heat that one, even we are heating, but it needs the presence of copper sulfide. So why it is needed? Because if you observe in a reactivity series, so if you observe in a reactivity series, the copper somehow we are considering in the moderate reactive, but sometimes it will show because it has the valence that is +2 or +3 state, so that is cupric or cuprous state. So due to that, it will act sometimes as the moderate and sometime as the low reactivity series. So that's the reason we can't heat directly that one to get the required metal. So for that you need the copper sulfide also. So if you heat in presence of copper sulfide, then it is possible to get a copper oxide or copper metal. So that is copper metal plus of remaining is SO2. That is the gas. Here also it is a gas. So now you have to balance the equation 2 that is for sulfur S and O. So that means it is to become 4, you have to add sulfur 1 and 2. So here it is a 1, oxygen is 2 here, so I'll add here 2 2s are 4, it will become. So if it become, so if you add 4 here, then 4 it will get increased, so we can't add this one. Okay, so here copper and copper are 4, sulfur is 1, oxygen is 2, so we have to balance for the oxygen. So first we will balance oxygen. So if you add oxygen here 2, then you have to add here 2 2s are 4, then again sulfur get increased. So I have somewhere okay, this is 2HCU now, this is 2CuO. So now you can observe this is the 4 5 6. So if you write this one is a 6, then you will get the equation. So the equation is 2Cu2O plus of Cu2S. In presence of copper sulfate, we are heating this one to get the pure, so which is the pure metal. This copper formed is the pure metal. This is the extraction of metals of low reactivity series. So now this is the first concept. Now we will move towards extraction of the metals in the middle, the activity series, whatever the metals are present at the middle, so that we will consider the active metals, the moderate active metals, how we can extract, from which method we can extract, that we will study. And for that you have to remember that the metals of the moderate reactive series are present in the form of ore, that is either metal carbonate or sulfide. If it is a metal sulfide, that is the same process, we are roasting. So roasting in presence of oxygen. If it is the carbonate form, then we are going for the calcination. Calcination is nothing but it is in a closed vessel, we are heating the metals, we are heating the ores. So in a closed vessel means little bit, there is no much more oxygen. So the calcination is the method where there is oxygen, and sulfide ores are we are heating that one in oxygen, that means it is the calcination. If you are heating that one in presence of oxygen, that is the roasting process. So just we will move it towards, that is extracting the metals in the middle of the activity series. And here some of the examples, that is this one, zinc, iron, lead and copper, these are considered as even aluminum we can consider here. These are the reactive, the moderate reactive metals, and these are present in the form, as we know, the metals of the medium reactive. So as I told, the metals of the medium reactivity may present in the form of, as it is in the present in the form of ore. So which type of ore? Either it is a sulfide ore or it is a carbonate ore. Carbonate ore. Okay, so either it is a sulfide ore or it is a carbonate ore. So one example we will take, that is the zinc metal, so which is the moderate reactive metal. So zinc sulfate, that is ZnS, or zinc carbonate. Zinc carbonate, so name of this one you can write as zinc sulfide. S means it is a sulfide, and zinc carbonate. And name of the ore, you have to remember that one, that is a zinc blende. And this one is calamine ore. So this is the name of the ore. Okay, so zinc sulfate can be called as zinc blende ore, and zinc carbonate can be called as calamite ore. So these are the moderate metals. These are the moderate active metals which is present in the form of sulfide ore and carbonate ore, or we can say zinc blende ore, calamine ore. So now we have to extract this one. From this we have to extract the metal. Yes, we have to extract the metal. So as it is a zinc sulfate, if the sulfate is there, which method, whether it is a calcination or roasting, we have to go for the roasting method. So roasting, and here it is a calcination method. Then you know that the zinc sulfide and zinc carbonate we can't separate easily. So as these are the sulfide and carbonate, we can't separate. First we have to convert that one to the metal oxide. Here also it is metal oxide. So that means there are the two steps. First there is a ore, you have to convert that one to the ore may be present in the form of sulfide or carbonate, that you have to convert. This metal ore you have to convert to the metal oxide. Then this metal oxide you have to convert. So this is the first step. Then in second step you have to convert metal oxide. So I'll write separately that metal oxide to the metal plus of something. So you have to convert this one. There are two steps in that. So the first step, one of the example we will consider here, only we will observe. So to get the metal, so the first zinc sulfide. So which method? The roasting method. So that means, so just write it here. So this is the zinc sulfide here, and here one of the example we will write zinc carbonate. So when as zinc carbonate is the calcination method. So what I told you, that is a calcination method means if there is no presence of air in a closed vessel, we are heating this carbonate. So in a closed vessel, if you heat the zinc carbonate, the ore or the calamine, if you heat, what it will give? The zinc oxide plus of zinc oxide, remaining is CO2. So zinc oxide and CO2 we will get, that is the metal oxide. This one is the metal oxide. And in case of zinc sulfide, so it is a roasting. So roasting means in excess of air. So in the presence of air, in the absence of air, or excess or absence of air, or you can say excess of air in this roasting case, absence of air, or in presence of air, in absence of air also you can write. So in presence of air means you have to write the excess of oxygen here. Yes, so that means it is the O2. So when you will heat this one, then there is a formation of zinc oxide plus of sulfur, and you have to balance the equation. Okay, you have to balance the equation here. So now you got the metal oxide. So what I told you, the first process is the ore is present in the form of sulfide and carbonate. If it is present in the sulfide, then by the roasting method, that means this method is called as roasting, and this method is called as calcination. So calcination. So if in presence of oxygen it is roasted, that is heated to give metal oxide. So this is the first step where we are getting metal oxide. So the ore is get converted to the metal oxide. Then second method. So that metal oxide we have to convert to the metal. So second step, first step is metal ore is get converted to the metal oxide. Second step, the metal oxide is get converted to the metal. Step, that is metal oxide converted to, you write the full sentence, okay, converted to the metal. So how it is possible? It has a particular method by using, this is also heating process, that particular name is blast furnace method. So what we are doing here, the metal, whatever the metal oxide we got, that we are heating, okay, that we are heating and we are reducing the oxygen from this. So whatever the metal oxide is there, we are using some reagents and we are heating in the blast furnace. So when you will heat, there is a reduction of oxygen will takes place. So when there is a reduction of oxygen, there is a formation of the metal compound. So there is a formation of metal compound. This blast furnace diagram I will show you. So this is the only picture of the blast furnace. So here what we are doing, the ore is in the form of, now the ore is in the form of oxide, yes. So that ore, as you know, these are the as you observed in the first case, that is the low reactive series, directly you will heat, the metal gets separated from the oxygen. But as this is related to the, now we are discussing about the moderate reactive series metal, is. So in case of moderate reactive series, it is not possible to easily detach the oxygen molecule, remove the oxygen, that means the reduction. Removal of oxygen is called reduction of the reaction. So remember, removal of the oxygen is a reduction of reaction. So as the ore is now in the form of metal oxide, so that is the zinc oxide, as you observed, when you add that one with coke, and limestone to the blast furnace upper side and use it for a smelting. Smelting is nothing but, write down the points, smelting is nothing but to removing the impurities and to get a pure metal, So ore is our zinc sulfide, then why there is a necessity of a coke? Coke is nothing but it is a carbon. Why there is a necessity? It is responsible for the reduction of oxygen. It is the responsible for a reduction reaction. It is responsible for to remove the oxygen from the zinc ore, that is the metal oxide. So from that oxygen we have to remove, for that we are using the coke. So it is not easy to remove the oxygen as it is a moderate reactive metals. So that's why the coke is the, why then only coke we are using? Because the coke is easily available and the cost is very less. So which is the cheapest that we will use for the separation. So reduction isn't. And what about the limestone? Why we are using the limestone? Whatever the impurities are there, that will collect together to form an flux. So which is the impurities combines, that is the gong particles that combines with the flux and it will form a slag formation. So the gong particles which reacts with a flux to give a slag, so that is removed here. The slag will come down and due to that it will be removed from this. So whatever the impurities are there, that will be removed from here, and the coke will help to make the metal oxide, it will convert the metal oxide to the metal. That means there is a reduction of reaction and the coke is called as reducing agent. Now the metal is in the pure form, that we will collect, we will take it from this one. So this is about blast furnace. And remember, in a moderate reactive series there are two steps. One is first the metal is present in the form of metal sulfate or the metal carbonate. So from that we are converting to the metal oxide. Then that metal oxide, that is ore, is reacted with the coke and limestone, where coke is the reducing agent and limestone, it helps to remove the impurities, that is the gong particles. It reacts with the flux to give a slag which is coming out. And here the smelting, what do you mean by the smelting? So the process of removing impurities and even formation of the removal of the metal, pure form of metal, that the whole process is called as a smelting. And then what about the blast furnace? This furnace is used for heating of the ore and to remove the metal from that. So this is especially used for the second one. So whatever I have explained there, that I will write metal oxide. This is the metal oxide. This whatever we got, that is our ore. So which is combined with coke and limestone. When it is heated in the blast furnace, we will get the metal. So for example, that with example we will write, that is first one is zinc oxide or zinc sulfide, you can write. So as it is a zinc sulfide is the ore which is reacted with the coke. So coke acts as a reducing agent here. Coke acts as a reducing agent. Okay, and limestone which is present in that only, so no need to write. So it is heated in the blast furnace to give zinc plus off. Here remaining is carbon and oxygen, so it is a carbon monoxide. It is like this. And here also zinc oxide will combine with coke to give zinc and carbon monoxide. So this is the reaction, how we can get a metal from this. This is a formed metal which is pure in form. So this is about second one. Then the question arises here, whether at every condition the reducing agent used is a coke. Is it at every condition? No, it is not possible. At every condition we can't use the coke as a reducing agent. So we can't it is not possible to use coke as a reducing agent at every condition. Only some of the condition we can use. So for that, so there is a one exception case, that is in case of manganese and chromium we can't use. So we'll write that one. We can't use coke as reducing agent. Then question arises, why can't we use? So we can use the reducing agent. Before that, for zinc we have used coke gas. Then for manganese and for chromium, it is not possible to use the coke as the reducing agent. Why? Because this coke is nothing but a carbon compound. So coke is nothing but a carbon, and carbon is less reactive. The carbon is less reactive compared to this manganese and chromium. If it is a less reactive, whether it is possible to displace the oxygen from that? Not possible. So if it is a more reactive, then only it is not possible. Then only it is possible. If it is a less reactive, then it is not possible. So that's the reason why can't we use the carbon as a reducing agent in case of manganese and the chromium. What's the reason for that? Because it is a less reactive. Then what we can use? Then what can be used? What can be used for manganese and chromium ore for reduction? That time we are using the aluminium powder. This is the very important concept. Okay, aluminium powder concept. So aluminium powder we are using as a reducing agent. In case of manganese and chromium. Why only aluminium? Aluminium and some other elements also there. So for example, sodium and calcium also can be used. So mostly we are using aluminium powder as a reducing agent. Because why? Because this aluminium is more reactive compared to manganese and chromium. Coke we are not using because it is less reactive. Aluminium we are using because it is more reactive. That you have to give reason. So for that we will write an example. So as I told, manganese. So manganese oxide. So MnO2, which will react. So instead of coke we have to write here aluminium powder, that is Al. It will give, that time as aluminium will act as a reducing agent. So this is the metal oxide, that is the manganese. So metal oxide get converted to the metal, that is a Mn plus of Al2O3 plus of heat. So you have to balance the equation. So just write it down. It is 3. If it is a 3, then it will become 3, and Al is 2. We will add here also. We will add 4 here. So 2 it will be 4, and oxygen is 3 to the 6, 3 to the 6, and heat. And remember, this Mn is in a liquid state. So this Mn is in, why I am making these marks means these are the very important. So what happens when manganese metal oxide, the manganese oxide reacts with the aluminium powder? So there is a more heat liberation. Due to the heat liberation, whatever the metal is there, usually the metals are solid in state. If it is solid in a state, but here you can observe that the manganese in liquid in state. Why manganese in liquid in state here? Why it is liquid in state? Because there is a liberation of heat. So there is a formation of, there is a exothermic reaction. Exothermic means heat is liberated. So liberation of heat is there. Due to that liberation of heat, the manganese will get converted to, will be in liquid state. So to remember this one. So this is known as the where the heat liberation process is there, and this is known as nothing but the thermit reaction. This reaction is nothing but a thermit reaction. Thermit. So it is nothing but heat. So heat, it is nothing but there is a liberation of heat, more heat. That time the metal is in presence of liquid form. That time the metal will get converted to the liquid form. That is a thermit reaction. So remaining concept we will discuss in next class. So just write down the homework question and try to write the answer with proper definition and send it to me.